So when we ended class, we looked at some different graphs as we were rolling a different number of dice. And what we saw there was that the center stayed about the same, regardless of how many dice we rolled. Our shape of our graph began to look like that bell-shaped normal curve, that it had this symmetric and unimodal look to it as we rolled more dice. And we also saw that the standard deviation got smaller as we rolled more dice. So what we're doing here now is taking these same ideas, very similar to what we did when we worked with the categorical variable. We're like pulling out those beads from those containers. We're seeing about how does this idea apply now to a quantitative variable. So under certain conditions, which we'll get to talk about here shortly about, we can say that y bar is approximately distributed normal with a mean of mu and a standard deviation of sigma over the square root of n. Now, this type of formula should look familiar. We saw something like this when we worked with categorical data. We had this up here, this sample distribution of the proportion. So we had certain conditions, and then we could say that p hat was approximately distributed normal, where this was our mean or our center, and this was our standard deviation. The difference here, so p hat was the sample proportion, y bar is the sample mean. P was the population proportion, mu is the population mean. So far, a pretty easy leap from the one to the other. Not as easy to see the leap. The standard deviation calculation is a little bit different, but in both places where we see is that sample size is showing up in the bottom, which is exactly what we saw. The more dice we rolled, so as n got bigger, our standard deviation got smaller. So a very similar idea to what we've had before. Now again, just for clarity, mu technically here is our mean of the y bar. This sigma over the square root of n is the standard deviation of y bar. Alright, so we've seen this idea before. What are these conditions that we need here now that we're talking about a quantitative variable instead of a categorical variable? Well, just as before, I still need my relatively random and unbiased sample that's not going anywhere. There's actually only two conditions we have here. The second one actually does have an or in it though. We either need to know that y is distributed normally or have a sample of at least 30. Now we can check to see if we have a sample of at least 30 pretty easily. This would mean that okay, if I'm rolling at least 30 dice at a time, we're okay. Now what does this y distributed normal part actually mean? That means that there's two different ways I can check this. The first one, it might tell me in the problem that something is normal. Or I can look at a graph, but it has to be the graph of the individual. So I'm not looking at rolling multiple dice. I'm looking at only rolling one dice. And it is looking like a bell curve already. So it's already symmetric and unimodal. But basically, if I already start with a graph that looks normal, y bar is going to stay normal. If I don't start with a graph that looks normal, if I sample enough people, or in a sense roll enough dice, then I can say that I'm going to be normal. Just as before as well, once I know it's normal, I can use so many other things that I've learned about it being normal. I can use my normal curve rule. Of course, I'm going to start with looking at my picture here. So my normal curve rule tells me to start at my mean, which is mu. And then I'm going to go 3 standard deviations in both directions. What is my standard deviation? That's sigma over the square root of n. Alright, and once I do that, if I go out 1 standard deviation in both directions, right? That's going to give me 68% of my sample mean. If I go out 2 standard deviations in both directions, that's going to give me 95% of my sample means. And if I go out 3 standard deviations, that's going to get me 99.7% of my sample means, of my Y bars. Okay, so that's going to hold. What else I can start working with is a Z. So in our very first set of notes, we had this Z was Y minus mu over sigma. Now what our Z is going to look like, instead of Y, we have a Y bar. So I have like the average of the group that I'm going to calculate. What am I going to subtract something off? I'm going to divide by something just as I did before. So going back, looking at my formula here, right, I want to subtract off the mean, which is mu, and I want to divide by the standard deviation, which is now the sigma over the square root of n. So still subtracting off mu, but now dividing by sigma over the square root of n. So a big difference between these two formulas, when we're using this first set of notes, we were always talking about an individual. What is the probability that a woman falls between a certain height? The probability that a house is between 2 certain prices. Right, this is always an individual, or in a sense, a thing that we were talking about. When we're working with this Z over here, we are now looking at the mean of n people, or a mean of a group. What is probably that the average height is a certain value is very different than the probability that a height is a certain value. So we're going to start next time by looking at an example to try to understand the big difference between these two. So in our next example, we will actually be using both formulas so that you can see the difference between what we were doing way back in the very first set of notes compared to what we're going to be doing now and why it's a little bit different.